Guys, let's move on to question G. In question G, you were given a graph, and let me draw it. You are given a graph, and which are your subway stations, nodes, in which nodes are your subway stations, and edges connecting these nodes are your subway lines, and each subway line has a color. So let's say these three edges are of color red, these of color blue, and these of color green. And it is given in the question that nodes connected by a single color are not disconnected. So for example, what they mean is that you will not get a subway line connecting, let's say, these two nodes which has color red, because in that case you'll have a disconnected subgraph. So you'll not encounter this case. It is guaranteed. So what you have to find is, you are given a starting node and an ending node. You have to move from here to here such that you use a minimum amount of, such that it passes through the minimum number of subway lines. So it's good. Let's say this was your starting node and this was your ending node. Let me take on the example given in the question. That will be better. Yes. So consider this graph. If you had to move from node 5 to node 4, you can simply take this path 5 to 2, 2 to 4, and you'll just encounter one subway line. And if your starting point was 5 and ending point was 1, then you'd have to take two subway lines, 5 to 2, 2 to 1. So that is going to be a minimum answer. So how do you approach this problem? So for that, before I explain the solution, you should be familiar with three concepts. So first one is graph transformation. That's something like graph transformation exists, that you can transform one graph into another graph based on your requirements. Other thing is coordinate compression. Not coordinate compression, it is not being exactly used here, but something like coordinate compression is being used here. And then shortest path using BFS. So if you know all three of them, familiar with them, well, good. If not, well, then you can learn them, get an idea from this video. So we can make few observations here. For example, if this is a graph, and this is, let's say, these are your red subway line, this is your blue subway line, this is your green subway line. Yes. So if your starting and ending lie in the same subgraph, you can easily move from there to here, and your answer will be 1. If your starting and ending were in different subgraphs, you'll have to use more than one one color lines, so your answer will be greater than 1, of course. So I mean, one observation that we can make is, in a particular subgraph, we can traverse between nodes, we can move to any of the nodes without changing our answer. So if, let's say, we are here, we can come here or here or here or here, wherever we like, without affecting our answer, and then move forward. So that is true for each of subgraphs of each color. So for example, we have 3 subgraphs. You can call it a subgraph or a system: red system, blue system, and green system. So all the nodes which are present in red system, all the nodes which are present in blue system, and all the nodes which are present in green system, we can traverse between each of them without affecting our answer. So it doesn't matter. So if starting and end both lie in the red system, good for us, answer is 1. I mean, they lie on a single, if they both lie on a single node, then our answer is going to be 0 because we don't have to traverse at all. But if they lie in different systems, let's say S lie here and E lies here, and then we have to see if red and blue systems are connected or not, and which means that is there a node which connects red system, I mean which has an edge which is red and which also has an edge which is blue. So in that case, this node is going to be present in both red and blue systems. Yes. So if that is the case, my red system and blue system will share an edge. There is going to be a path between red and blue, and if that is not the case, let's say there's no connection between red and blue subgraphs, but there's a connection between red and green and blue. So in that case, your answer will be 3 because from red you'll move to green, and from green you will go to blue. So you will be using 3 different colors to move from source to end. So from this observation, we can think of changing this graph. We are not changing this graph, but introducing new nodes to it. So for example, new nodes which are going to denote our colors. So if let's say this node represent, let this node represent color red, let this node represent color green, and let this node represent color blue, and then you have your initial nodes 1 to n, and we'll add edges as follows. If I had an edge of color red coming out of node 1, so I'll connect this node 1 to node red, and if I had along with red I also had an edge of color green coming out of node 1, I'll connect it to green as well, and same thing I'll do with all of these nodes. Whichever edges were basically, if a node is part of whichever subsystems, red, green, blue will add an edge to it. So this is going to be our new transformed graph. And our answer, the minimum distance, the minimum, not distance, but the minimum number of, we want minimum numbers of subway lines to be used. So let's say, let me draw this graph and show it to you. So I have red, blue, and green. One is connected to green, 2 is connected to green and red, 3 is connected to green and blue, 4 is connected to red, 5 is connected to red, and 6 is connected to blue and green. So now let's say we have to move in this question. In this example, we have to move from 1 to 3. So 1 to 3. Both of them lie in the green subsystem, so our answer is going to be 1. But if in this graph, in the transformed graph, if we start from 1 and try to go to 3, so the shortest path in this graph is going to be first we move from node 1 to node G, and then from node G to node 3. So our length of shortest path in the transformed graph is going to be 2 for if we have to move from 1 to 3. If we had to move from 1 to 5 in our transformed graph, first we'll move from 1 to green, and then we'll move from green to 2, and from 2 we'll move to red, and from red we'll move to 5. So this is going to be our shortest path. 1 to 5, and its length is going to be 4. In the first case, we were just using one color, and in the second case, we are using two colors. So if you can, the idea here is that the shortest path in the transformed graph, if it is, let x be the shortest path in the transformed graph, so our answer in the actual graph is going to be x by 2. I mean, it is easy to observe if you try run the test cases. During the, I did not prove it. I still don't know how to prove it, and even if proof is required or not, I guessed it. I kind of guessed it, and it worked. But it is easy to see. It's not that complicated to visualize. So your answer is going to be the length by 2, whichever length that you found in the transform graph. So now, how will you find the length, the shortest path in the transform graph? The edges here are weightless. They're not weighted. So the shortest path can be calculated using BFS. And if you don't know how to calculate shortest path using BFS, I mean, you can. There are many tutorials on YouTube. You can find out. It's one of the first thing that they teach you when you learn. First thing that you learn when you start to learn BFS. So the next thing is, how are you going to create this graph? Because you have these nodes with you, 1 2 3 4 5, and you have these color nodes, red, blue, green, black, white. So I mean, you cannot just while creating a graph, you cannot just push characters into it. You'll have to convert these colors into numbers, and also they are given you, they provided to you in the form of numbers. So let's say colors that are given to you are 5, 11, 13, 14. So first you will sort them and transform this array into a newer array. First we'll sort them. In place of 5 we'll put 1, in place of 11 we'll put 2, 13, 3, 14, 4. And since you already have 1 to n nodes present with you, you'll just add n to each of these numbers. So these new numbers are going to be your new nodes. So initially you had n nodes. Now you have, which were numbered from 1 to n. Now you have 1 plus. Now you have n plus c nodes. Let's say you have k colors with you. So you have n plus k nodes with you, numbered from 1 to n plus k. And then you'll add the edges accordingly, like I showed you here. Whichever that node belongs to, whichever subgraphs, you'll just add that node into that color. Add an edge between that node and that node representing that color. So this is the part. I mean, this is not exactly coordinate compression, but that's how coordinate compression is done. So that's why I mentioned coordinate compression before. So I'll summarize everything. You have a graph with you. You turn it into a different graph. Then you apply BFS. Find the shortest path between S to E. You'll get an answer. You'll get a shortest path. And your actual answer is going to be whatever shortest path that you got, whatever its length. It's going to be, you have to divide it by 2. This is going to be your answer. So I hope conceptually it is clear, and I'll show you my code. Yes, so this is, I have a set where I'm storing all these colors, and then this is my CP map where I assign numbers to those colors, 1 2 3 4 5. After that, this is my graph. In this part, I add edges into my graph. This is where I create my graph, which I talked about. A to C, A is my first node, B is my second node, and C is my color. So an edge goes between A to C, between A and C, and an edge goes between B and C. Once my graph is formed, I apply a simple BFS, and whatever distance I get of my whatever this en represents the total distance between starting and ending node, I just divide it by 2 and print my answer. So that is all. I hope that that you understood the solution. Okay, thanks. Bye.